Today we the biomedical imaging in our class. Okay, so in this first slide of this particular slide, I have shown some skeleton, and on the hand of this skeleton in the ring finger, there is some object. Okay, so this particular figure has some historical advantage, like that this particular figure was the first ever taken X-ray by Dr. William Röntgen, and this is actually showing his wife's ring finger is showing. Okay, so this is the first X-ray imaged in the history, world of history. Okay, so let us discuss the medical imaging in detail right now. Now, why imaging? So this is the visual representation in the interior of the body for clinical analysis. So this has some aspect, obviously, importance obviously, is that while the physicians try to diagnose some diseases only by assumption that there may be some tumors, or there may be some cancerous cell, maybe. But while we go for imaging, these particular things are getting clearer, that what is the uh, actual tumor, and what is the space it has been taken, and how it has been looked like, what the volume it has been taken by the particular tumor, or whether the particular cell has been really infected with cancer or not. This has been getting clear by the imaging. Okay, so the physicians get much more clearer by seeing the figure, by seeing the picture, obviously, rather than only the guessing. Okay, so the visual representation of the interior of the body for clinical analysis is very important. And next, after detection, that the how much big or how deep that particular tumor is, the better medical intervention is obviously possible. That that until unless the physician does not know what is its depth, what is the penetration of the cancer cell, the particular physician cannot treat the severity of this particular infection. Okay, so when he sees that up to how many cells, or up to how much severity the cancer cell has been affected to the particular cell, it is not very easy for the physician to treat that particular cell. Okay, so better medical intervention is obviously another aspect of or importance of imaging. Okay, and the third point is the visual representation of the function of some organs or tissues, obviously. So supposed to be embryo, its actual improvement, or how it is growing inside the tomb, etc., everything will be visualized in the imaging. Okay, in the physiology part. Okay, so let us now see how many types of imaging are there in medical instrumentation. Okay, so all the particular type of imaging is not possible, being the human body is the concern. Okay, so we are having this number of, or these techniques can be involved for the imaging in the medical purpose. Okay, so the X-ray is the ancient most technique of imaging. Okay, and then the CT scan, actually it is the 3D imaging of X-ray, 3D representation, while X-ray is the 2D representation, CT scan is the 3D representation. So there is some problem in X-ray, obviously, as it is the ancient most technique. Obviously, there will be some problem in X-ray detection. Okay, and CT scan is the technique where we try to eliminate that particular problem which we face in X-ray. It is a 2D, And in CT scan, it is a 3D imaging. Obviously, in 3D, the particular dimension of the tumors or other cells, we can definitely can detect much more clearly, right? So the CT scan is the 3D imaging. Okay, then the ultrasonograph in USG, it is the USG. Then MRI, magnetic resonance imaging. Then we have the nuclear imaging like PET, positron emission tomography, or SPECT, likewise. Then we will have the thermal imaging for our concern. Then the echocardiogram, and some microwave imaging. So all these type of imagings are possible. The techniques are possible in medical imaging purpose. Okay. So is there any queries? You may ask me anytime. Okay, so now we will discuss what is X-ray. Okay, so in X-ray, this is the ancient most technique of imaging, and this was discovered by Wilhelm Röntgen in the year of 1895. Okay, and this is obviously a century year ago. So whatever, this was to diagnose some bony structure of the human body only. So there is obviously some uh, some problem or some restrictions, you may know, you may call it, that this can diagnose only some bony structure of the human body. Okay, not the other things it can detect. So the tissues and the blood flows, it cannot detect. Okay, so this has some restrictions in X-ray. It can only diagnose the bony structure. Okay, so now some basics of X-ray, and based on the fact that various anatomical structure of a body have different densities of the X-ray. When the X-rays from a point source penetrate a section of body, the internal body structure absorbs the varying amount of radiation, and the radiation that leaves the body has some spatial intensity variation. So an image of the internal structure of the body will be formed while we record that particular spatial intensity variation. That is the technique. Okay, so in medical diagnostic properties of X-ray, we will have the capability to penetrate the matter coupled with differential absorption observed in the various materials. Okay, so this particular differential absorption uh, will be much more than the intensity, or the particular image will be much more clarity. Okay, so we will discuss this particular point afterwards. And now next point is the ability to produce luminescence and its photographic emulations. Okay, so these two are the medical diagnostic properties of X-ray. Now the arrangement, how to snap or how to photograph that X-ray. So X-ray intensity distribution is visualized by a suitable device to be called some photographic film. Okay, and a shadow image is generated that corresponds to the X-ray density in the body section. Okay, so over here in this particular figure, I have tried to show you guys that let me zoom it much further. Okay, so let us see the image very much clearly. So in this, in this particular image, in this particular image, okay, So this is the particular image receptor plane, okay? Or you can call this particular plane as the photographic plane, okay? Now, this is the X-ray source, and the beam has been penetrating through different body parts or body elements like bone. There may be some air inside our body. There may be some different tissues. There may be the tumor inside our body. Okay. So this particular X-ray source is penetrating the body. And see this column. This is actually the beam collimator. Okay. So there will be obviously some beam angle. With that angle, it is incidenting on the human body, and the human body consisting of the bony structure, some tumor maybe inside it, maybe different tissues inside it, maybe air, maybe blood and other type of elements inside the human body. Okay, so this particular X-ray is actually penetrating the all these things. And see over here at the right side of this image receptor plane, we can clearly see the spatial distribution of intensity is varying due to different body elements. So see over here, due to the bony structure, the bone has absorbed maximum of the X-ray, okay? And after absorbing, it has only a few of its energy has the has the uh, uh, okay, over here. Okay, so this has the only the absorbed varying amount of radiation. Okay, so in this point, I mentioned that when the X-rays from a point of source penetrate the section of the body, the internal body structure absorbs the varying amount of radiation. So on that particular figure, we have seen that the bony structure is absorbing maximum of the X-ray energy. Okay, and see over here, the radiation that leaves the body has some special intensity variation. An image of the internal structure of the body will be formed. So obviously over here in this particular image, you can see again that after going through or penetrating the bone, the minimum amount of the energy, it has been shown in the special distribution of intensity. Okay, and over here you can see for the air being the material inside our body. So see over here, this is the maximum energy level. It has been shown on the special distribution of intensity, and supposed to be for tumor, this has this level of special distribution intensity. So suppose this particular image clearly shows that as the bone is the solid material, okay, so this will absorb maximum amount of energy from the X-ray. Okay, so this is the thing. So now the X-ray picture, I have mentioned all the points over here, that the X-ray picture is called some radiograph, which is usually obtained on some photographic film placed in the image plane. And the skeletal structures are easy to visualize, and even some untrained eye sometimes observe the fracture and other bone abnormalities. So the X-ray picture is very much clear to the physician, and it is very much clear to obviously the untrained eye who is not a physician. He too can, or he or she can sometimes very or easily determine whether there is any abnormalities in the bone structure, bony structure, or if there are any fractures in this particular bone, if there is. Okay, so it is clearly visible by using radiograph. Now some applications of X-ray is that On bony structure, we know that these can be easily determined whether the bone has been fractured or if there is any abnormalities are there or not. And apart from this application, there are some more application like the chest radiographs, is that the examining of lungs and heart. Though I mentioned that the unless the bony structure, it is very difficult to understand what is uh, actually going on in the image of X-ray. But there are some technique to visualize the non-bony structure. That means the lungs and heart. We can also visualize or photograph these lungs and heart by chest radiographs by injecting some contrast element inside the heart or lung. Okay, so the thing is that to chest radiograph, we will use some technique that the air enclosed in the respiratory tract, obviously, and bronchi will seen as negative contrast. Okay, so air to be some negative contrast, and the pulmonary vessels which will contain the blood will be seen as positive contrast against the air filled lung tissues. Okay, so here the technique or the trick is that the air enclosed in the respiratory tract we will see as the negative contrast. Okay, and the pulmonary vessels which will contain the blood, we will treat that these are the positive contrast uh, in respect to the air. Okay, so the different types of lung infections are accompanied by characteristics changes enable a diagnosis to be made from location, size, and extent of shadow. Okay, now the heart examinations are performed by taking frontal and lateral films. The evaluation is performed partly by total heart volume and partly on the basis of any other changes in shape. Okay, so these are some photographs of the lungs. Okay, inside the lungs we can see the particular respiratory tracts which is clearly shown in this figure as negative contrast, and pulmonary vessels are seen as some positive contrast. Obviously these are white. Okay, so by this contrast difference we can easily determine whether if there is any abnormality in this particular uh, lungs of the human. Okay, so this is very clearly seen if there is any blockages or any other abnormalities inside it. Okay, by using the positive contrast as to be taken as the pulmonary vessels, and inside the blood we will take the positive contrast, and the respiratory tract inside it there is some air, we will take it as some negative contrast. So using the contrast difference we can easily determine whether if there is any abnormalities or not. And now in heart examination, see there is we will take the same contrast ratio or the contrast difference to determine whether there is any abnormalities inside the heart or not. Okay, so the heart is clearly visible by using the contrast difference only. Okay, so this is the chest radiograph. Now if there is any questions, you guys have any questions, please ask me. Now the second application is angiography. Okay, so if the circulatory system is checked by injecting some water soluble organic compound of iodine for making a good contrast medium and then examined by X-ray, this technique is called angiogram. Okay, so obviously this is not possible to take the negative contrast, the air, and the positive contrast as the pulmonary vessels inside it there is some blood, we will take it some positive contrast. This is always not possible. Maybe there is some always the this particular contrast difference is always not possible. Okay, so if we inject some dye water soluble organic compound of iodine for making the good contrast medium, and we will inject it inside our blood vessels, then the particular examination or determination by the X-ray will be much more advantageous. And by using this technique, which we call angiography, the particular detection gets much more clearer. Okay, so now the coronary angiography, it is the test for coronary vessels of the heart. We will obviously first initially inject some water soluble organic compound of iodine, okay, inside the coronary vessel of the heart, and then we will take the X-ray. Okay, and the radiograph we will call coronary angiography. Then the angiocardiography, inside the heart, we will try to push that particular organic water soluble organic compound. Okay, and in the cerebral angiography, inside our brain, we will push that particular organic solution inside the brain to observe by using the X-ray. Then myelography, inside the spinal canal, we will push or inject the water soluble organic compound. And mammography for the breast. Okay, so these are some examples of angiography. Okay, so see over here, this is the structure of the eye, human eye, and if there is any blockage inside the any vessel, this is obviously clearly visible. This is some picture taken from human brain. If there is, and these are the water soluble particular dye has been injected, then photograph. Okay, if there is any abnormalities, it could be found very easily. And this is the spinal cord, and inside the cord, spinal cord, we have injected the dye and taken photograph, X-ray photography. And uh, this is the lungs. Okay, and the final case is the mammogram. Okay, now there is some basic physics regarding the X-ray, the nature of X-ray. The X-ray is some electromagnetic radiation located at the low wavelength end of electromagnetic spectrum. Its wavelength is 10 to the power minus 10 meter for medical diagnosis. Okay, and the propagation speed is the same like the speed of light. Number 3 is the unaffected by electrical or magnetic field. This is one advantage, very advantageous point of X-ray, is that it cannot be affected by the interference of electrical or magnetic field. Okay, so this has obviously some advantage. Now the packets of energy, as per the quantum theory, electromagnetic radiations consist of some photons and conceived as the packets of energy. Okay, so it has been transmitted from one place to another place in some packets of energy, not a single quantity. Okay, so this is that is why the uh, transmission, we call it that the packets of energy is being transmitted. Okay, now the wavelength of the photon energy is given by the energy equation is E equal to h nu, that is equal to h c by lambda. Okay, where h is the Planck's constant, is 6.32 into 10 to the power minus 32 joule second. Okay, c is the photon propagation velocity. Okay, and nu is the radiation frequency, and lambda is the wavelength of the particular EM waveform or X-ray. Okay, So the X-ray properties are like that. It is of short wavelength. It will uh, it will have some extremely high energy and penetrates through materials which absorbs and reflects some visible lights. And after reflection, it forms the basis of the use of X-rays for radiography and their potential danger. Okay, so the potential danger is that if you use the X-ray in a particular organ for different times, okay, so there is a chance that the particular organ can have some impact. Okay, so this is obviously some dangerous for the human body, and this should not be done. Okay, now the absorption depends on the density of the matter. Absorption depends on the density of the matter, how much solid it is. The absorption is dependent on that. So on the very first or second figure in the arrangement of snap, I have shown that particular figure. You, if you can remember that after the receptor plane, we saw that the image distribution intensity was the lowest for the bone. Okay, so the absorption depends on the density. As that bone has the maximum density, so the minimum amount of energy was got from the image receptor plane. Okay, so the intensity was the lowest over there, if you can remember. Okay, now the X-ray produces some secondary radiation through which they pass. This is very much important, the secondary radiation. Let us see how the secondary radiation is important. Okay, so the secondary radiation will consist of some scattered radiation, has some practical importance, and characteristic radiation, and some electrons. Okay, so after the absorption, okay, the X-ray will produce some secondary radiation through which they pass. Okay, so this will have some scattered radiation, number one. Number two is the characteristic radiation, and number three is the electrons. Okay, so you can guess how the secondary radiation is important. Okay, now we will discuss these things after some time. Okay, in detail, what is the secondary radiation and how the scattered radiation has the practical importance. Okay, now the another properties in X-ray of X-ray is that it produces ionization in gases. It has some influence, it will influence the electric properties of liquids and solids, and ionization property is used for radiation measuring instruments. Okay, so this is another application, you may say, of X-ray, is that the ionization property uh, is to measure the is for some measurement. Okay, now it will produce some fluorescence in certain material to help them emit light. The units of X-ray is the Röntgen, as per the name of Wilhelm Röntgen, the discoverer of X-ray. Okay, it is adopted by International Commission of Radiology Units and Measurements, and abbreviated as capital R. Okay, so 1 Röntgen is equal to amount of X radiation to produce 2.08 into 10 to the power 9 ion pairs per centimeter cube of air at STP. Okay, 0 degree Celsius and 760 millimeter of mercury at sea level and at latitude 45 degree. Okay, so there is obviously some milliröntgen is 1 upon 1000 Röntgen. Micro Röntgen is 10 to the power minus 6 Röntgen. So this is 1 unit. So this unit of X radiation based on the ionization produced by the rays. Okay, second one is the rad, the unit of absorbed dose by a matter. So 1 rad is the radiation dose which will result in an energy absorption of 1 into 10 to the power minus 2 joule per kg in the irradiated material. So 1 rad is approximately equal to 1 Roentgen for soft tissues. Okay. Now the third unit for X radiation, X-ray is the D. Okay. D is absorbed dose, known as absorbed dose. D is equal to, defined as the F into R. Okay. R is Roentgen and F is some proportionality constant which will depend upon the composition of irradiated material and the quality of radiation of beam. Okay. So the value of F for air is 0.87 rad per Roentgen, and for soft tissues it is 1 rad per Roentgen, and for bone F is larger but significantly decreases with the applied voltage of X-ray. Okay. Now the dose equivalent DE, H dot DE, is defined as the product of absorbed dose D and the modifying quality factor QF, such that DE is equal to QF into D. Okay. So these are some units of X-ray. Now X-ray generation, how to generate the X-rays. When the electrons collide a matter at a very high speed and thus suddenly stopped, X-ray will produce. So the energy possessed by the electrons appear from the site of collision as some parcel of energy in the form of highly penetrating electromagnetic waves, which are to be called X-rays. Okay. X-ray is of many different wavelengths, together forms a continuous spectrum. Okay. Now the X-rays are produced in specially constructed glass tube, and inside the glass tube, the construction of glass tube is that a source inside the glass tube for the production of electrons. Okay. An energy source to accelerate the electrons, to speed up the electrons. Okay. There is some free electron path, a means of focusing the electron beam, and the obviously the beam collimator we call it, and the device to stop the electrons. Okay. So this is the block diagram of X-ray machine. Okay. This particular block diagram we will discuss later in our class. Okay. So let us try to find out the X-ray machine, the construction of the glass. Okay. So, okay. Let us first see the X-ray tube. So this is the stationary anode tube. What is stationary and what is rotating? Why it is rotating? What is the disadvantage of stationary? We will discuss it later. But preliminarily, we will discuss the anode tube. Okay, so inside the anode tube, okay, this is the anode tube, and this particular anode tube is that the tube is some vacuum diode. Okay. So the electrons are generated by thermoionic emission from the filament of the tube. Okay. So the electrons are being generated from here. Okay, from here by some thermoionic emission from the filament of the tube. This is the tungsten filament. Okay, this is the tungsten filament, and we are sorry. Okay, we are applying the voltage over here. Okay, so this is the cathode, and this is the filament construction, and the construction of the filament is that there are some helical arrangement of some metal. Okay, so we will discuss it later. Now these particular electrons are being formed, and due to vacuum in nature, these particular electrons will flow from this cathode to the tungsten anode, okay, or the copper anode. And inside the copper anode, the target is made up of tungsten. Why? Again, we will discuss later. So let us see, the tube is some vacuum diode. The electrons are generated by thermionic emission from the filament of the tube. So the electron stream is electrostatically focused on the target on the anode by suitably shaped cathode cup. Okay. So suitably shaped means what? That the particular generated electron stream will be focused on the anode. So that is why it is suitably shaped. Okay. And the kinetic energy of the electrons impinging on the target is converted into X-rays, and electrons emitted by the hot filament become the current carrier across the tube. As the electrons is being transmitted, we know that the conventional current I will be flowing at the opposite of the direction of the electron flow. So that is why there will be some current flow or current carrier the tube becomes. So it is possible to independently set the tube current by adjusting the filament temperature and the tube voltage. Obviously, as the current is flowing from one end to another end, obviously there will be some voltage difference, otherwise no current should flow. So the tube voltage, we can this particular current is can be controlled by the tube voltage by adjusting the primary voltage only. Okay, so today's class up to this. Thank you very much.